Good morning. Good morning, OCP. It's great to be here. I just wanted to start by thanking OCP and thanking all of you. I feel like OCP has really become the premier venue and organization where we come together to advance at-scale computing. And I think we have a great deal of work in front of us, and that's mostly what I wanted to talk about today. So if we want to contemplate for a moment the future of at-scale computing, data centers, cloud computing, I think three words come to mind. The first is scalable. I think we have succeeded in creating a world where our users can imagine that computing is this infinite resource, infinitely scalable that they can access at any time. Of course, we know it's not infinite, and it's a great deal of work to make that illusion happen. And in the future, we're going to have to double it in the next 3 to 5 years, and then we're going to have to double it yet again. And how do we do that while making sure everything is sustainable? And the final word is security, but I didn't put it on the foil because I'm not going to talk about it today. These challenges are really immense and kind of scary when we think about it, but I think it's useful to look at what we've accomplished in the past. We have an amazing track record in this industry of delivering energy efficiency, of delivering more compute for less energy. And a recent study in Science magazine showed that from the period from 2010 to 2018, we reduced the energy intensity of data centers worldwide by 20% each and every year. That's an astounding accomplishment. That means we increased compute instances by 550% while only growing electricity consumption by 6%. It's sort of mind-blowing. And I think it's illustrative to think about how we did that so that we can chart a course for how we can continue in the future. And the first piece of it is, of course, Moore's Law. We've been able to build more efficient computers. We've been able to deliver more performance per watt, per dollar. A compute node today delivering the same amount of compute as 2010, is less than a quarter of the energy consumption. But that alone was not enough to deliver those kind of results. We had to invest in very large-scale computing. The shift to hyperscale introduced tremendous efficiencies, according to these researchers. And what's also exciting, and I noticed at last year's summit, was that technologies pioneered at the hyperscale are diffusing out into the edge and the smaller deployments. So the innovations that happen at hyperscale have an impact even beyond. And then finally, according to this article, the rise of virtualization revolutionized the efficiency of data centers by allocating hardware more efficiently than ever. And I think the key point there is that hardware and software working together accomplishes a great deal. So if we think about this amazing journey we've been on, I think it points us directly to the future that we need to pursue. First and foremost, we need to continue with Moore's Law. And I'm not going to talk to you about EUV and ribbon FETs and that sort of thing, but I think as an industry, we have to work together to unleash Moore's Law. Second, hyperscale efficiency. We can't be satisfied with what we've accomplished already. And I'm going to point out a couple of technologies that I think point the way to some significant gains in the future. And then finally, inspired by the progress from virtualization, hardware-aware software and software-hardware collaboration generally is going to yield outsized gains that are really going to drive the future. So anyway, I'm going to talk about each of these in turn. So let's start with Moore's Law. Not surprising that the Intel guy is going to talk about Moore's Law. So we know that increased scaling in semiconductors is going to give us more performance per watt. But it's becoming increasingly challenging for systems to take advantage of it. And that's the piece that I think we together have to work on. If we think of what the system has to do to realize Moore's Law, there's really kind of 4 things. The first is I/O and memory bandwidth. And here we've made a great deal of progress. We have DDR5 hitting the market, and DDR5 is scaling really well. So memory bandwidth has moved forward well. We have PCI Express Gen 5, which is scaling I/O. We have new technologies like CXL, which bring coherency to I/O and give us a lot of tools to create innovative, composable systems, expand memory, do those sort of things. So that part I feel very good about. We also have to bring power into the machine. I also feel like we've made a great deal of innovations into powering these semiconductors. And then finally, we have to make innovations in cooling them, because today we're sort of reaching the limits of cooling, and I'm going to talk about that a bit later. And then finally, One of the biggest barriers to taking full advantage of Moore's law is resiliency and the blast radius that a system has for the overall operation. If you go from 128 core systems to 512 or 1,000, just looking out over the next several years, how do we make that reliable? How do we make it such that software and hardware can deliver mission-critical results? That's a real challenge. And one of the areas that is going to be talked about a lot in the next year is component resilience. And it's an area we've been investing in heavily at Intel, and we're proud to be working with OCP on the new server component resilience workstream with a bunch of our key partners here in OCP, including Google. We have done a lot up until now in terms of silicon architecture, in terms of silicon testing, in terms of system-level testing, and we've also realized that you need fleet-level testing throughout the life of semiconductors in order to assure the level of resilient operation that these new systems demand. But when we look into the future, we see that that's not enough, and that's the important role of this work stream. I believe that software and hardware are going to have to collaborate together to provide the level of resiliency and the level of reliability that these new large-scale systems of the future are going to require. And I'm looking forward to the panel discussion on Thursday, where we're going to dive into this in more detail. I'm sure it'll be exciting. Second, how do we expand the gains we've made with hyperscale? I believe there's two key technologies. There's probably actually 10, but there's two that I'm going to talk about. And the first is modularity. The way we design servers is undergoing a revolution, and the way we've done it in the past is simply not going to be sufficient for the future, either from a sustainability point of view or a scalability point of view. And the way we cool systems with air is running out of steam, and I think we need to embrace the radical step of immersion cooling. Neither of these things are going to happen on their own. They're going to require OCP, and they're going to require companies in this industry to come together and drive change. So I first wanted to talk about modularity. So I'm super excited to see that OCP is leading here with the DCMHS, the Data Center Modular Hardware System. So HP, AMD, Dell, Google, Meta, Microsoft, and Intel have all worked on this specification, and it's become increasingly mature. And what modularity does for us is it allows us to reuse components, which is very sustainable. It allows us to engage in a circular supply chain. It allows us to optimize PCBs, which are the #1 contributor to the embodied carbon of the server. So there's a bunch of sustainability values. But it also allows us to save R&D costs and bring new systems to market faster. Because once we've validated the individual building blocks, we can literally build dozens of servers based on the same robust component. So to better illustrate that, I've got a video to show you what DCMHS is all about. So let's roll the video. Thank you. It's a really exciting vision, but I really want to make the point that it's not vision. It's here. This is our 4th gen Xeon scalable processor-based dual socket full width DCMHS reference design. So this is available for development today. And we also have a density optimized offering that I have here. And then our partners at Jabil with Intel have developed a full-on density optimized server, the Mustang. This is going to be in production in 2023. So it's reality. I believe that DCMHS is going to be rapidly adopted by the industry because it offers so much. And the collaboration between these companies has assured that this specification is robust to the needs of the industry. You can use it to build edge servers. You can build it an enterprise server or a cloud server. I/O can be on the front. I/O can be on the back. What used to be unique designs are now built from the same building blocks. There are 6 specifications, hundreds of pages of technical details. I believe it's ready to go and ramp. So we've been working hard on that, but let's talk about cooling. So air cooling has been with us for a long time, and people have talked about liquid cooling for a long time, and it's always that thing we're going to do in the future. I believe we've reached a time where liquid cooling has to play a much bigger role in the data center, if for no other reason than the PUE capability that liquid cooling brings. And if you're in a humid climate, the numbers here don't even begin to scratch the surface, right? Evaporative cooling is really challenged in some of those climates. But the PUE of 1.03 doesn't even begin to scratch the surface of the value. Once we've moved, especially to immersion cooling, we can take the fans completely out of the system. Fan power is a major contributor to overall data center energy consumption. And let's not forget about the water consumption. In North America alone, data centers consume hundreds of millions of gallons of water per year. And all of that can go away. So it's a much more sustainable capability. So why haven't we already been there? Well, because it's kind of hard. There's a lot of problems to solve. The cost of entry are too high. And though a bunch of companies, from very large ones to innovative startups, are joining this ecosystem to solve those problems, we still have work to do. I believe there's been more energy around immersion cooling in the last year than I've ever heard in a very long time, and I think the time is now. One of the problems that we need to solve, however, are the liquids themselves. So the liquids touch every component. Every component somehow needs to be qualified to work with the liquid, and it's a problem. So we need to standardize the liquids so that systems know what to expect from their liquid. Intel's leading here. We are bringing out a specification with partners through OCP, and we are eager to engage in the rest of the industry to make liquid standardization happen so that we can scale immersion cooling. There's other problems we need to solve too, but this is foundational. Because of our ability to get a good liquid ecosystem going, Intel is going to be able to now offer warranties on our components with immersion cooling, which is a big step forward. So I'm really excited about it. We're ready to go on immersion cooling. But that's not all. Finally, and I think the most important task for the future is getting to hardware-aware software. I don't know about how you guys feel, but I feel like sometimes the software developers and the hardware developers are on different planets. But the actuality is we're on the same planet, and we've got to be responsive to the needs of this planet. And hardware is not the only important thing when it comes to driving energy efficiency. And yes, we can leverage Moore's law, and we can get 10, 15% improvements in energy efficiency. But if hardware and software partner together, we can get massive gains. I believe that there's a 10x opportunity if hardware and software work together. And there's a lot of ways to pursue, including continuing to improve virtualization. But the one that I wanted to focus on here today is workload acceleration. And certainly, I'm not the first person to bring up workload acceleration, and many large companies have leveraged it in specific cases, but we've struggled to scale it. And I think we have to have new energy behind bringing software and hardware together. Now, in our upcoming product, the 4th generation Xeon Scalable processor, we've invested a lot in accelerators, and these are some examples of what we can do. For example, encryption, which is already accelerated, we are accelerating it further with 4.2x gains. Data compression, up to 2x gains. Inference, one of the biggest workloads worldwide, we can accelerate up to 30x. This is a big deal. And if we work together, we can make it happen. But I think the mechanisms that we have with the hardware living on one planet and software living on another planet isn't getting us there fast enough. Accelerated computing is responsible computing. And we really have to start thinking of it that way. When we check in software into open source projects, we need to understand the carbon footprint that we're creating. And when we're designing accelerators and hardware, we need to understand how we plug into that software community that's going to use it so we can actually realize these kinds of benefits. We've done it before, we can do it again. So really, I think the key message is we have enormous opportunities to drive efficiency in the data center. Most of those align well with our economic goals of bringing TCO down and performance up. But to really get the gains and to scale them fast enough for what the world needs, we have to really work together. So we have to continue with Moore's Law, and we're going to keep working on that at Intel. But we have to build systems that can take advantage of those benefits. We have to continue hyperscale. We have to deliver on modularity so that we can deliver the benefits that it brings. We have to manage this transition to liquid cooling, which I think is going to be tough. But when I talk to people in the industry, some people say we're ready to go now. Some people say it's going to take 3 to 5 years. But I don't hear anybody saying that we don't have to do it. So I'm super excited about that opportunity. And then finally, hardware and software working together. I would challenge you and OCP to help us find the way. And with that, thanks and enjoy the show.